Hey everybody, is that working?
Yeah, it looks like so.
Yeah,
Sounds
okay.
good. Yeah.
So hi, my name is Rob Noble, for those who don't know me. I'm a department head of the Department of Physics, Engineering Physics and Astronomy, and my mask is fogging up my glasses. So welcome to the first colloquium of the 2021-2022 year. And the first time we've come together in a room for over 18 months, or about 18 months, with faculty, grad students, staff, undergrads, all together. So welcome. The colloquium, for those who don't know, is the weekly time when we invite interesting speakers and scientists to come tell us about their work at a level accessible to all of us, regardless of our subspecialty. It's a time for us to get together and learn something new. And I hope everyone comes to as many of these colloquia as they can. It really is a key part of the academic, the intellectual life of the department. And it's also a key time to just get together, chat with colleagues. We won't have coffee and donuts this year, but we will still get together. And thanks very much to the organizing committee for putting together an interesting slate of talks. It is really great to see a lot of people here in person. Virtual meetings have kept us together and teaching and learning physics, but it's still different actually being in a room together. I'd like to acknowledge that Queens and Kingston are situated on the traditional Anishinaabe and Haudenosaunee territory. We are grateful to live, learn, and gather together on these lands. So, welcome.
Hello? Okay. All right. My name is Nahi Park. Many of you may not know me, and because I'm newly hired faculty from the November last year, so I basically stay in my home until very recently. So I'm running around serving. I don't know anything other than my office at this point. So it's really great to see people in space. And I would like to introduce our speaker today, Dr. Miriam Diamond. She is a brilliant scientist, and she got her bachelor from Charlton University and got the Master of Science in University of Waterloo. And then she got PhD in University of Toronto. And then she went on to research at the Stanford Linear Accelerator Center. And throughout her research through this time, she was working on studying the dark matter searches with the accelerator signal. So she was looking at the atlas to search for the dark matter hint there. And then she came back to Canada and now become an assistant professor in University of Toronto and also faculty member of Arthur McDonald Institution. And she now is working in the Snow Lab, focused on the searching for the low mass dark matter searches with the SuperCDMS. And she is really brilliant and is widely known enough that she now has 2020 Polanyi Prize in Physics for the exceptional early career researcher in Ontario. So it's really honored and very nice to have her here as opening colloquium of this semester. So can you do?
Thank you so much. Just double checking, can everyone hear me? All right, it is so wonderful to be here in person with you all, and thank you so much for showing up, even though there was no free coffee and donuts. I know just how important free food is and free caffeine is for students. In fact, when I was working at Stanford Linear Accelerator, partway through my time there, I took over as experimental seminar coordinator. And at about that same time, we had a glitch in our budget that suddenly the account to which we would charge the coffee and cookies for the seminars was unavailable for a little while. And I thought, oh dear, now I'm going to look like a terrible seminar coordinator because the attendance is just going to drop off very steeply. And so I crowdsourced my problem, and some of my California friends in Silicon Valley said, well, do what everybody else does here when they run out of funding for something. Just innovate something incredibly nerdy and make it go viral and figure out how to make money off of it. So I ended up doing stand-up quantum comedy routines at clubs in San Francisco and San Jose. And the tips from these routines ended up paying the coffee and cookies budget for a few seminars until we got the administrative hassles sorted out. So not only beware of bean counters in accounting, but beware of coffee bean counters. Anyway, So if you get really desperate, you can also go onto a wonderful website called darkmattercoffee.com. So there, not only can you get coffee, but it's dark matter coffee. All right, so my mission today is to convince you all to join the dark side, specifically the dark matter beyond the standard model. And I hope that I can convince you all that our our solid state detectors for low mass dark matter searches will take over the galaxy. Will be the basis for the next major particle physics discovery. All right, so let's start with what is the Rebel Alliance? What is dark matter? Our current best theories of the universe tell us that approximately 68% of it is made up of something called dark energy, 27% is made up of something called dark matter, and everything that we call ordinary matter is the rest of that rather small slice. What we call ordinary matter, we have this beautiful standard model of particle physics which describes its most fundamental building blocks and the way that they interact with one another. So almost all of the matter that we encounter around us in everyday life is actually made of up quarks and down quarks, which combine to make protons and neutrons in atoms. And then there's electrons buzzing around those. It turns out that there are actually 4 more types of quarks, which we call flavors. Similarly, the electron has 2 heavier cousins called the muon and the tau. And there are also these mischievous little particles called neutrinos, which were the basis for Dr. Art McDonald's Nobel Prize. So those are the matter particles. Then there's also the force carrier particles, which are called bosons. And fairly recently at Large Hadron Collider, we discovered the Higgs boson, which was a major missing piece to the standard model, which we had predicted should exist, but we weren't able to actually find until about a decade ago. So we have this beautiful standard model, but it only describes this little sliver of the universe. And so the big question that I have devoted the past several years, I won't say how many years, of my life to investigating is what makes up this dark matter. Dark energy is a whole other fascinating field which I don't specialize in. That would be a whole other colloquium talk. So we're going to just leave aside dark energy for now and concentrate on dark matter. Our leading theory is that dark matter is made up of some new particle or new set of particles that is not in the standard model. This, by the way, is my dark matter guinea piggy. When I was doing all of these conferences virtually, I would actually bring the little guinea piggy in front of the camera. But I didn't want to try and stow away the guinea pig on the train and bring him with me here. So I just have a photo of the little guy. So first of all, we want to know what exactly is he. But also, we want to answer additional questions like what mechanisms set the amount of dark matter relative to so-called regular matter in our universe, and how did this amount change over cosmic timescales since the Big Bang? So I'm going to briefly introduce you to our leading theory and sort of simplest, most general story that we can tell for how dark matter, or DM for short, might have been produced in the early universe. So the idea here is that very, very shortly after the Big Bang, the universe was extremely hot, and it was just this soup of subatomic particles all over the place. And at this time, the dark matter particles, which are denoted by these little Greek symbols chi, were in thermal equilibrium with the standard model particles, which we denote here by F, standing for fermion. And so you had constantly these interactions going on where a dark matter and a dark antimatter particle would actually combine into this soup, and then the energy from that collision would cause a pair of standard model particles to pop out of the soup. And the very same thing could happen in reverse, where the standard model particles can annihilate to dark matter particles. And so, so this was at an extremely hot temperature. Literally, we can't even get our heads around how hot this was. A very small fraction of a moment after the Big Bang. And then as time went on, the universe cooled, so the temperature went down, and we can make these plots of temperature or equivalently time, but they are reversed. So as time goes forward, the temperature actually goes down. Okay, and of the number density of dark matter particles. And so as time goes on and the temperature drops and the universe cools, what actually happens is that this soup of standard model particles no longer has enough average energy to produce pairs of dark matter particles. And so now this reaction is only going one way. And the dark matter particles, meanwhile, could still annihilate with each other to create standard model particles. So the dark matter number density drops and drops and drops until actually the universe expands so much and gets so cold that the dark matter stops even annihilating with itself. And this is known as the freeze-out time. And so then here, dark matter particles stop getting converted into standard model particles, and we are left with this so-called relic abundance of dark matter sitting around in the universe, which we still see today, presumably. And so what exactly are these dark matter particles? Well, we actually have a whole zoo of possibilities of what these could be. This is my personal little zoo of guinea piggies. But one particularly popular leading candidate over the past few decades is known as the WIMP, short for weakly interacting massive particle. By the way, don't try to call one of your guinea pigs a wimp or they get very offended at you. Then they start squeaking and whistling, and you really don't want that. So the key about these weakly interacting massive particles is we hypothesize that their mass is approximately at the so-called weak scale, so that's about 100 times the mass of a proton. And if you plug that in to some formulas for actually calculating what the relic abundance of the dark matter particle should be, and you plug in some more relevant particle physics quantities, such as the mass of the Z boson and the average cross-section times speed of these dark matter particles moving around, you get exactly the correct relic abundance. And so this was known as the so-called WIMP miracle. And so we came up with several, I suppose you could call them wimpy search strategies for how to actually see these WIMPs in the lab. And there is what I call complementarity between the different types of experiments in that they each take a different approach at probing for these WIMPs. So one category of experiments, which, for example, I worked on at the ATLAS experiment at the Large Hadron Collider, is that we take standard model particles and we accelerate them to very, very close to the speed of light, and we smash them together. And so here we are sort of trying to replicate, again, those conditions that we had in the very early universe where they would annihilate to actually produce dark matter particles. And then we hope to produce enough dark matter particles that even if we only detect a very, very, very tiny fraction of them, that we do eventually see some of them. Then there's so-called indirect detection experiments, which I actually have not worked on personally, but many of my talented colleagues have, where we basically wait for dark matter particles to collide with each other somewhere in outer space. And we hope to detect the standard model products of those collisions using things like space probes. So if you like launching stuff into outer space, this is really cool. And then there's the category of experiments that I work on right now, which are called direct detection, where we essentially wait for a dark matter particle to come wandering in from outer space and collide with a detector that we have set up that is, of course, made of standard model particles. And we hope that every once in a while that dark matter particle will give our detector a tiny, tiny little nudge, and that we will actually be able to detect that nudge as the dark matter particle then just goes on its way. We have constructed a few decades worth of these experiments now, and we actually have not found WIMPs in the mass range where we had most expected to find them. So we often make these plots in what we call parameter space, where on one axis here we plot the mass of the hypothesized dark matter particle. 1 GeV here is about the mass of a proton, and a little bit over 100 GeV here is approximately the weak scale. And then we plot what we call the interaction cross-section, which is essentially a measure of how much the dark matter interacts with the standard model. And by its very nature, this interaction has to be very, very feeble. Otherwise, we would have seen the dark matter already. So these numbers are very, very small. And each of the lines that are solid on this plot corresponds to an experiment that has already been performed, and it has ruled out dark matter particles in all of the parameter space above and to the right of it. And then the dotted lines are ones that are planned for the next few years, including some of the ones that I work on here. And then here in yellow is what we call the neutrino floor. And so it turns out that if a dark matter particle is located below this so-called neutrino floor in parameter space, its interactions with the standard model will actually be so feeble that they will get completely swamped by interactions of neutrinos. And so even with very, very sensitive detectors, we're going to have a lot of trouble actually seeing the dark matter because we'll just get swamped with neutrino counts. So as I warn my students, don't fall through the floor, don't fall through the neutrino floor. So now that we have sort of ruled out so much of this parameter space, what happens next? This is where I encourage you all to come to the solid dark side. So what I'm going to do for the rest of this seminar is take you through the basic principles of direct detection experiments, and specifically the challenge of using these for dark matter particles with masses below a GeV, in other words, lighter than a proton. And then I want to show you a little bit about why solid-state types of detectors are particularly promising. These include cryogenic semiconductor and scintillating crystals and charge-coupled devices. And then I will show you limits that we have actually been able to set on various candidates in this dark matter zoo using the solid-state devices. All right, so let's start with the basic principles of building a Death Star, of conducting direct detection experiments. So we are all on this wonderful spaceship called Earth, hurtling through space, because not only are we going around the sun, but the sun is going around the center of our galaxy at a speed of about 270 kilometers per second. And we hypothesize that there is this so-called dark matter halo, so this sort of haze of dark matter particles in which our entire visible Milky Way galaxy is embedded. So as we move through the galaxy, we should actually be getting collisions of galactic dark matter particles coming at us, or equivalently us coming at the particles. When we set up a little detector here on Earth, there should be this constant flux of dark matter particles hitting it. So when dark matter particles collide with standard model particles in the detector or in the target, the dark matter particles might occasionally be absorbed by the standard model particles or cause nuclear or electronic recoils. So a nuclear recoil, it's exactly what it sounds like. The dark matter particle comes in, it bonks into the nucleus, sets the nucleus ringing or gets it excited, and then goes off on its way. An electron recoil, the dark matter comes in and actually hits an electron and puts that electron into an excited state, or maybe kicks it out of its atom altogether. So there is a big challenge to using this type of detection technique at the GeV scale or lower. And the reason that this is important is that WIMP miracle that I told you about earlier, although it was originally investigated in the mass range of sort of a GeV to tens of TeV, a TeV being 1,000 GeV, tera electron volt, it turns out that it also does work at least down to about a mega electron volt. So that's about twice the mass of the electron, or 1,000th the mass of the proton. And so this is a regime that we call light dark matter. So the thermal relic WIMP-like scheme does work in this range, just that we also have to allow for new lower mass so-called dark mediators or dark force carriers. So this is literally the dark side of the force. So the idea is that in the same way that, for example, the photon mediates the standard model electromagnetism, we would have, for example, a dark photon that mediates some sort of dark electromagnetism, which basically only acts between dark matter particles. But every once in a while, we could have a dark photon turn into a photon, or vice versa. So there'd be a very, very tiny interaction caused by that mixing between the dark force carrier and the standard model force carriers. So this is a really sort of fascinating area of parameter space to look into, but it also really stretches the traditional, as I call them, wimpy direct detection searches, where much of the sensitivity actually comes from nuclear recoil. And so the reason is that if you look at sort of a cartoon version of those plots in parameter space that I showed you earlier, where we've sort of already ruled out this gray area, if you try to push the mass of the particle down, you end up with the difficulty that the energy is actually too small to cause a nuclear recoil. And similarly, if you try and look for feebler and feebler interactions, in other words, if you try and push this limit downward, well, you run into a problem that the rate of dark matter interactions that you actually see in your detector is inversely proportional to the mass. So if we want to look not only for this light dark matter, but even more challenging potentially, is to look for these dark mediators at sort of the milli-electron volt to kilo-electron volt scale. We also want to detect so-called dark absorption processes, where the dark mediator actually gets absorbed by a standard model particle. And so this is a plot here that sort of shows you in cartoon form in green the mass ranges that the next generation of experiments sort of over the next few years are going to look for, where the traditional WIMPy searches were up here in the top right corner. And then in blue, longer term, so you can see we keep trying to push lower and lower in terms of mass. Okay, so these are more sort of cartoon plots in that parameter space where the sort of yellow, does that show as yellow or orange, light brown? Okay, whatever, is the current bound that we have, and then green is what we hope to achieve in near-term experiments, and then blue, again, is the far-term. Where the left-hand plot here, this is for nuclear scattering, and then the center here is scattering off of electrons, and then the right-hand plot here is an example of absorption. So you can see that with all these detection techniques, we are really trying to push into a wider area of parameter space despite all of the significant physics and engineering challenges that this poses us. And one of the ways that we hope to do that is by utilizing solid state detectors. So what I'm showing you here is sort of a cartoon diagram of the three main so-called channels that we can use to try and detect dark matter interactions. So one is by actually detecting the heat or the quanta of vibration, which is known as phonons, that are produced when a dark matter particle interacts with the detector. One is by detecting charge, for example, if an electron has been dislodged from its atom. And one is by detecting light, or the photons that are emitted. And as you can see, you basically can only get two out of these three channels working in the same detector, or you can choose just one of them. You really, or at least we haven't managed to build a single detector that harnesses all three. So the different types of detector technologies are sort of shown around the rim of this triangle. And the ones that I've highlighted in blue here are solid state technologies. So these are really promising for a couple of reasons. One is that they have a really low minimum energy threshold on the phonon channels. So that means we can use them to detect even a very, very small amount of vibration. So they are not subject to nasty little effects called quenching that reduce ionization and scintillation signals at low energy. But it's good to try to pair this phonon channel with either a charge or a light channel, because the phonon signal is actually generally independent of the type of dark matter particle that is doing the interacting. While ionization or scintillation channels can actually provide discrimination between electron recoils and nuclear recoils, and that helps tell us what kind of particle this dark matter might have been. Okay, so as I mentioned, we can sort of rely on an elastic nuclear recoil signal for dark matter masses down to about a few GeV. And this is a similar threshold to the other major type of technology, which you'll see here, which is basically using giant chambers of liquid noble gases. But if we try and go below a GeV, we find that the momentum and the energy transfer is very inefficient to the nucleus, so doesn't cause nuclear recoils very well. So our alternatives are to look at either inelastic processes or to look at electron recoils. And so then if you start thinking about, okay, what electron recoil energies and what dark matter masses can we actually look at? So for noble liquid types of detectors, this tends to be in the range of about 5 MeV dark matter mass, and then if you try to go lower than that, it sort of peters out. With some different solid state technologies that I've highlighted here, we can go down to hundreds of keV, or with some speculative and R&D technologies, even down to a few keV. So the ones that I'm going to mostly focus on here are the ones that I currently work with, which are semiconductors and scintillators. And so here we are probing down to energy deposits of about the electron volt scale. Okay, so the first one of these technologies that I'm going to show you is cryogenic semiconductor crystals. So this is an actual picture here of what the semiconductor crystal looks like. These are typically made out of either silicon or germanium. And then it goes into this nice looking housing. And essentially, how this works is that we wait for a dark matter particle to wander in. It goes right through the shielding, goes into the crystal, and then every once in a while, it's going to cause a recoil. And right when that recoil happens, there's going to be phonons emitted. You can get thermal and you can get non-thermal phonons. And then those phonons bounce around the crystal until eventually they land on a crystal face. And on the face of the crystal, we have put these phonon sensors. And so when the phonon lands on the sensor, it increases the temperature of that sensor just a tiny, tiny bit. And it is that increase in temperature that actually generates the signal that we see. So because of how sensitive these detectors are, we not only have to put shielding around them, but we need to operate them in a very radio pure environment. Otherwise, we would constantly get particles from ambient radioactivity setting off this lattice. So we also, in order to reduce the thermal vibrations in the lattice, have to operate these at a very cold temperature, hence the cryogenic in the title, down to literally tens of millikelvin. So this is very, very close to absolute zero. And the devices themselves are actually not that big. Each of these crystals is sort of on the scale of tens of grams. So one of the first of this type of experiment to be constructed was called Edelweiss. You'll see throughout this talk there's some rather interesting acronyms that physicists managed to come up with. So here, this was a French collaboration, as you can see. They used a combination of phonon and ionization signals to allow them to discriminate between nuclear and electron recoils in the detector. And how they did that is for each event, they measured what's called the ionization yield. So this is just the ratio of the amount of energy deposition in the ionization channel to the amount in the phonon channel. And for nuclear recoils, that ionization yield is normalized to be approximately 1, whereas for electron recoils, it's much lower. And then there's the experiment which I work on. It was, the first generation of it was called CDMS, Cryogenic Dark Matter Search. There have been multiple generations of this experiment, so then we went on to SuperCDMS. Yeah, you can see how creative we are. So the last version of SuperCDMS ran underground in a mine called Sudan in Minnesota. And the one that we're currently building, the next generation SuperCDMS, is being installed right now to run at SNOLAB. So here we have a phonon channel and a charge channel. It is similar in some ways to Edelweiss, but we can actually apply a bias voltage across the crystal. And so what happens then is that if you generate an electron-hole pair in an interaction inside the crystal, the field causes the electron to drift one way and the hole to drift the other. And there is an effect called the Luke effect, by which these charged particles traveling through the crystal actually emit more phonons. So we essentially get this phonon cascade. We have the total phonon energy measured using what we call transition edge sensors on the edges of the crystals, read out by squids. Squids is not what I had for lunch. I did have lunch at the university club, but there was no calamari, which is good because calamari is what you get if something malfunctions and you fry a squid. You don't want that happening in your electronics. No, squid is actually a superconducting quantum interference device. Okay, and then we not only measure the total phonon energy in one channel, but also we have another channel that measures the number of electron-hole pairs, or in other words, the charge, using so-called high electron mobility transistors. So by applying this bias voltage, we lower significantly the recoil energy threshold because we generate so many more phonons. But we can no longer do discrimination between electron recoil and nuclear recoil, and we lose sort of what we call the true calorimetry because there's a bunch of this Luke phonon energy that does not get included in the primary recoil energy. And we are currently working on a set of prototypes. hvev is short for high voltage electron volt range. And these are gram scale devices, so they're even smaller than the ones I showed you earlier. And they are so sensitive that they can actually detect down to a single electron hole pair. Okay, and in runs at surface test facilities that we've done so far, very recently, just a few days of live time with a gram scale device yielded near world leading dark matter limits in certain models. I'm now going to show you a variation on this type of technology, which is a cryogenic scintillating crystal. For example, CREST-3. Cryogenic rare event search with superconducting thermometers. And so this one also uses a crystal, but it's a different type of crystal. This, for example, is calcium tungstate. It also has TESs, which are read out by squids for the phonons. But simultaneously with the primary phonon signal, it doesn't read out the charge, it reads out scintillation light, okay? Because this particular type of crystal is scintillating. And so the light is collected in a separate absorber, and you can look at the light yield, which is just the ratio of the light energy to the phonon energy to get electron recoil versus nuclear recoil discrimination. Once again, this has to be run at very, very cold temperatures. Once again, you can see here from the two bands the electron recoil versus nuclear recoil discrimination. All right, so now I'm going to show you sort of a different category of solid-state devices, and these are known as charge-coupled devices, CCDs. And what's really cool is that almost every one of you, I guarantee you, has CCDs in your cell phone camera, okay? These are basically silicon devices. And so what happens is you have a whole bunch of these little silicon pixels. In the case of your camera, when light hits it, it generates a little electronic signal, and by putting together all these pixels, you get an image. What we do is we actually bury this somewhere very dark underground, and we wait for dark matter to come and knock into a pixel. And so when that happens, you actually promote an electron in the silicon from so-called the valence band to the conduction band. The latest generation of these charge-coupled devices actually has literally 1 or 2 electron resolution. So that's really amazing. And they can run at quite a bit higher temperatures than the devices I showed you earlier, so something like 130 or 140 Kelvin. And so the hope is that even though the dark matter would probably only create 1 or maybe a few electrons in a pixel, the CCDs are now sensitive enough that you can actually see that. So there is an experiment at Snow Lab currently called Damik, short for dark matter in CCDs. And so this operates with shielding in a vacuum underground, and you form an image by basically exposing this camera for several hours, followed by doing a readout 1 by 1 of the pixels. And then you can see you can get these nice distributions of charge in the pixels. And then there's the next generation of that, which is called sub-electron noise skipper CCD experimental instrument, or Sensei. And so these skippers are basically a new type of CCD which measures each individual pixel something like 800 times without actually disturbing the quantum state of that pixel, which is very kind of challenging from an engineering point of view. So you get essentially a more reliable readout, and you can do it either in a continuous readout mode or in a periodic mode. Finally, for the last few minutes of this talk, I'm going to be showing you some limits that have been placed recently by solid-state devices in dark matter parameter space. So I will start with nuclear recoil. So on the vertical axis here is the dark matter nucleon interaction cross-section, and here on the horizontal axis is the dark matter mass. So of these lines that you can see here, all but one of them, the one called NewsG here, was made using a solid-state device. And similarly, for electron recoil, the so-called xenon limits here, xenon 110 and xenon 10, were made by a different type of experiment that used, well, it's just what it sounds like. It's a giant tank of xenon. All of these other lines here, Sensei, Damik, and then SuperCDMS hvev prototype devices made these lines, and you can see that they are what is covering the low part of this mass regime down to something like 1 MeV. We can look also for absorption of the dark force carriers. So one particularly popular example of this dark force carrier called the dark photon. And so here again, you can see SuperCDMS devices, hvev, Damik, covering the low end of this parameter space. One of the things that I love about astroparticle physics, by the way, is that you sometimes also get astrophysics limits on these plots. So this little gray area is actually disfavored because if you had dark photons in this area, the sun would not shine the way it does, which is kind of cool. This is another candidate from the particle zoo called an axion. Axion also doesn't work very well as a name for a guinea pig, I discovered. I'm not sure why. Guinea pigs just don't like that name. And so you can see here a huge chunk of low mass parameter space from a very recent SuperCDMS hvev prototype device. And then these are little critters called LIPs. I told you there'd be some nice acronyms here. Lightly ionizing particles. And so these are essentially hypothesized particles that would have a standard model electromagnetic charge that is a very, very tiny fraction of what the electron has. And just to confuse you, we actually like to plot it as the inverse of the fractional EM charge instead of the EM charge. So the higher 1 over F is, the lower the amount of charge is. You can see that CDMS, for example, and another version of it called CDMS Lite is what set a couple of these lines here. Okay, so hopefully I have convinced you all to come to the solid dark side. We have cookies, hopefully dark chocolate cookies or with chocolate chips in them. So you've seen that direct detection of WIMP-like or light WIMP-like dark matter at the GeV and sub-GeV scale through nuclear recoil and or electron recoil is a well-motivated challenge, especially when it is accompanied by searches for low-mass mediators, the dark side of the force, at the EV to KeV scale through dark absorption. So it is solid-state technologies for the Death Star that will crush the Rebel Alliance. I mean, solid-state technologies including cryogenic semiconductor and scintillating crystals and charge-coupled devices, which provide many advantages for such searches, as we have very recently demonstrated in some world-leading limits that have come out over the last few years on low-mass recoils, as well as dark photons, axions, LIPs, etc. And we have R&D and prototype devices which are promising further very exciting discovery potential in the near future. Thank you.
We need to use a microphone for the remotely connecting people. Yeah, is it? Okay. And thank you very much for a really great talk. I really like all the Star Wars references and all that. So any questions from audience?
I'll ask a very naive question. You said that there's this neutrino floor. What happens if we're below the neutrino floor? Is there a way to potentially detect dark matter, or is it hopeless?
That's actually a really, really good question.
Wait a second, Miriam. Would you mind repeating the question?
Okay, yes. So you asked what happens below the neutrino floor. If it turns out that that is where dark matter actually is, can we think of a way to maybe detect it, or is it completely hopeless? So I would say it is not completely hopeless, partially because physicists are endlessly ingenious and partly because we're very stubborn. So one of the ideas that we are looking at is to use so-called directional detection. So the idea behind this is that the vast majority of the neutrinos that we would be detecting actually come from the sun. Okay, they're solar neutrinos. But as we move around in the dark matter halo, depending on which direction we're going, right, as we're moving into the halo, that's where most of the dark matter particles should be coming from. So if we can find a way to tag what direction the incoming dark matter particle came in at, and then if we accumulate enough statistics and we find, okay, what is the general direction that most of them are coming from, right? The ones that are sort of coming from the sun, we can say, okay, these are more likely to be neutrinos. The thing is, well, it's difficult enough to detect a dark matter particle in the first place. To also figure out what direction it was coming in at is sort of an additional challenge. But if we can do something like sort of try to reconstruct the track along which it came, or if we can use something about the kinematics of the collision, so what direction does some recoil product come out in, So I would say directional detectors are probably our best chance right now of going down below the neutrino floor.
Oh, yeah, I was checking if there was no question yet. Sarah?
Hi. You mentioned that some of your cryogenic crystal detectors have to be operated at this millikelvin temperature. I was wondering what that cooling process is like. I've heard that to get down there you have to use lasers. I was wondering if once you cool down to there, how long does it actually stay at that temperature, or is it more of a continuous process, and does that actually affect your detectors at all?
Okay, so basically the question was about how do we get down to a few millikelvins in temperature that's needed to run some of our cryogenic experiments. Do we need to use something like lasers for it? And does the process of cooling it down like that actually affect the experimental apparatus in some way that we would see in our detection? Okay, first thing that I will say is cryogenics is indeed a very large part of our experiment. Getting the cryogenic setup installed and getting it working correctly is really difficult. Just recently, actually, as we were getting going again on the installation of some of our equipment in SuperCDMS, we did spring a leak in the cryogenic system, and that is quite difficult to isolate and then fix. So no, actually we do not use lasers. We use things like dilution refrigerators. So these use basically superfluid liquid helium. And in terms of making sure that the cryogenics equipment doesn't generate a fake signal in the detector, yeah, so this is actually really important that the system be designed and isolated in a way that, you know, we don't have something ringing or some kind of noise coming out of one of the cryostats that we would see in the detectors. So yeah, it's definitely an engineering challenge.
Thank you.
Any other question? Over there?
Yeah, hi. You spoke a little about how the sun puts some limits on your plots. Could you talk a bit more on how the sun affects the dark photons and how that places limits on that?
Sure. Okay. So this question is about how the sun and the way that it shines puts limits on dark photons. So basically, we have at least what we think is a very well understood solar model of all of the nuclear processes that go on in the sun, how much light that should be giving off, and then what spectrum we actually see from the sun, and so forth. If you have a bunch of the photons that are originally emitted from the sun turning into dark photons, that gets messed up.
Okay, any more questions?
Yes, I just wanted to ask, there is an experiment right now which is at its very early stages, which is trying to build an array of accelerometers, very sensitive ones though, and it is trying to measure a track of a dark matter which interacts with it. So my question was, once we know how we have those tracks, once we can detect those, how do you find that from which direction it is coming? I mean, so how would you go with that? Like, suppose you have the track, you know the track. So how would you trace back to from which direction it was coming at you?
Okay, so you're basically asking if you had an array of accelerometers and you got a track that's in that array, how would you reconstruct from the track the direction?
Because you just mentioned that the direction would play a very important role if it was below the neutrino floor.
Yes, to help us get from the neutrino floor, yeah. So, I mean, the details of what kind of tracking algorithm you need for what kind of experiment depends a lot on the technology that's used and the layout. So it's very hard for me to answer that without actually knowing what kind of equipment you have. But I mean, generally what you end up doing is some sort of a fit, okay, where one of the things that you have to do is these Monte Carlo simulations or theoretical simulations of, okay, if a dark matter particle came from here and was coming in at this angle, then what would that look like in your detector? And then you compare what you actually see to sort of Monte Carlo results, and you see, okay, how closely does this match here? So there's usually some sort of fitting and statistics process, something that takes into account all of the experimental uncertainties, because of course you never get an exact number, say, out of each accelerometer, right? You only get a measurement with some error, and then there's some percentage of the time where you'll probably just get a completely wrong measurement from noise or whatever. So yeah, so there's sort of some fitting and then some statistics-based process you have to go through.
Thank you.
Okay, we have one question from remote session person. It's from Tony, and I don't understand this question, but I hope they do. So the question is, why do the skippers need to read 800 times? What does that mean?
Oh, why do the skippers? Okay. So when we were talking earlier about charge-coupled devices and skippers, yeah. So basically the way in which a charge-coupled device works, right, is that it kicks out one electrons or multiple electrons from a pixel. And then the challenge is, okay, how do you actually measure or observe those electrons? And when you're down at the level of a single electron in a single pixel, you get quantum effects that mess you up. This is due to the uncertainty principle, essentially. And so if you simply do one measurement on a pixel and you ask, is there an electron here or is there not, okay? Every so often you'll get the wrong answer, essentially. But if you could make this same measurement, say 800 times over, where you observe the state of the system each time, and then you sort of say, okay, what's the answer that I've gotten the majority of the time, then you're pretty much guaranteed to get the right answer. The problem is, how do you observe that system without actually disturbing its state? And so that's what the skipper CCD basically does, and it's sort of a way of moving the electron back and forth between one potential well and another. And so that each time you sort of juggle it back and forth, you can get a measurement of it, but you don't lose it, so to speak. And so it's just basically a way of getting around the mischievousness of quantum physics.
Thank you. I think we have maybe one more question. We have time for one more question. Oh wow. Okay. You will talk with her, so maybe I will go to the students if you don't.
Yeah, you were talking about, to discriminate with the neutrino floor, you will use directionality, but that will only work for sub-GeV kind of GeV dark matter, right? Because you have the solar neutrinos, and you can have like the win-win. But when you go to higher masses, and you have like other neutrino sources like the DCMB and atmospheric and supernova, then directionality is not like much a thing that you can do, right, with those sorts of neutrinos. So how would you go about it? Like, do you just reduce uncertainties, and that's the best we can do?
Okay, so you're asking what to do for directional detection for higher neutrino energies if you have things like atmospheric neutrinos, or were you saying supernova neutrinos?
Yeah, so for the higher masses of dark matter.
Okay. So supernova neutrinos, they sort of appear in a cluster in time when the supernova goes off. So you can usually sort of get rid of those. Atmospheric neutrinos, I mean, so for those of you who are wondering what's going on with atmospheric neutrinos, basically there's cosmic ray interactions that happen in Earth's atmosphere all the time that send out these showers of particles. So there's some charged particle from outer space that collides with the atmosphere, makes a shower of other particles, and many of those particles are neutrinos, and then those come down to Earth. Of course, because neutrinos are so mischievous, if you get a shower like that happening on the other side of the Earth from you, you can't actually get neutrinos coming all the way through the Earth at you. That being said, there is a difference still that you can usually generally tell that your atmospheric neutrinos are coming vaguely from overhead, and there's yeah, I mean, there's a lot of things we haven't worked out, honestly, about how well direct detection would work against certain types of things in different spectra. Generally, it is for, so let me show you again the plots of the neutrino floor here. I sort of tend to look at what happens on the left-hand side of this plot, like with the solar neutrinos from some beryllium and boron 8. The neutrino floor is, literally higher here, right? So yeah, I don't tend to do as much stuff that happens here. What's nice is that if you get to like 100 GeV though, you actually have a better chance of finding dark matter through other, say, collider-based detection techniques. And so then you can sort of have a second approach to come at it by the time you're getting to like 100 GeV or something like that.
Okay, I think we need to wrap the session. Thank you very much for our Oh yeah, of course. And thank you very much for everyone to come here. And the graduate students, you will have 1 hour just solely dedicated for you to talk to the speaker in the lounge. So whoever is interested actually can go and meet with the speaker for 1 hour from now.